Hello guys, I just want to talk about PN junction semiconductor diode in this video. In the last video, we made the circuit and we see how this circuit works. We realized this diode can conduct electricity in one direction from this positive side to the negative side, not on the other direction. If you haven't seen that video, it would be good if you can watch that video. And this is a PN junction semiconductor diode. Over here you can see this side with the silver line is negative side and the other side is positive. So always electric current pass from the positive to the negative side, not the other way. That's what this PN junction diode do. And let's see what's inside. We will see how a PN junction semiconductor diode work. To learn that, we need to know what is a semiconductor. And a famous example of semiconductor is silicon. Silicon, everybody know what is silicon? So many rocks are made of silicon, all the sand made of silicon. So silicon is one of the abundant materials in the world. It's almost everywhere. That's a semiconductor. Then there's another semiconductor, which is germanium, which is another one. Then there is a gallium arsenide, which is another semiconductor. But we won't be discussing anything about germanium or gallium arsenic semiconductors. We will stick to silicon semiconductor because which is used most commonly, and most of the semiconductor devices are like diodes or transistors or IC chips or microprocessors. Everything is made of silicon, and silicon is the most common. So what is a semiconductor? Semiconductor is not a metal like a copper or anything. Also, it's not like an insulator like plastic or anything. Its conductivity comes between an insulator or a perfect conductor. In pure form, 100% silicon actually acts as an insulator. But if we add some impurity into the silicon crystal, it can act as a conductor. Its conductivity will get improved dramatically. So a semiconductor can be conductive if it has some impurity in it, and if it is pure, it cannot conduct electricity. So that's the semiconductor. So how a silicon atom looks like. A silicon atom has a nucleus, a positively charged nucleus, and it has so many electrons around it. I'm just drawing the outer shell. Outer shell has 4 electrons in its outer orbit. So that's the silicon atom. That's a very bad drawing. Anyway, that's 4 electrons. You get the idea. That's like 4 electrons at the outer shell of the silicon atom. And these 4 electrons are shared with another 4 silicon atom in a pure semiconductor silicon crystal. So there's no free electrons to conduct electricity. In order for material to conduct electricity, it should have some free electrons in its crystal or in its surface. So silicon in its pure form doesn't have any free electrons, so it cannot conduct electricity. But we can make it conductive by adding some impurities, as I said. See, we have our silicon atom here, which has 4 electrons in its outer shell. And if I'm adding an impurity, which is also called doping, adding an impurity to a semiconductor, a pure semiconductor is called dopings. I'm adding an impurity like phosphorus, which has not 4, but it has 5 electrons outer shell. So 1, 2, 3, 4, 5 the extra electrons here. So this phosphorus can share its 4 electrons with silicon atoms around it, but the fifth one leave free. So this one is free, so it can conduct an electricity. This electron can conduct an electricity, helps to conduct electricity. So what we end up with, so what happened when we add an atom like phosphorus to a silicon semiconductor, pure silicon semiconductor, what happens, we end up with so many free electrons in the crystal, and that is called an n-type semiconductor. So this is our semiconductor crystal. We doped with a pentavalent, that's a fancy term to use, an element with 5 electrons on the outer shell. So when we dope a silicon crystal like this with a phosphorus atom or phosphorus, it ends up with so many free electrons in the crystal lattice, like that. So that is this negative sign shows like the free electron, by the way. So what happens? So this is a crystal with so many free electrons. That's basically like a metal. A metal has so many free electrons on it, and if you connect it to a battery or something, it will conduct electricity. So let's connect to a battery like that. It will conduct electricity like that. So this is a negative terminal supply electrons, and these electrons will push these electrons to the other end, and the electron flow this way. So the current flow this way. So it's just a convention that current is always flows opposite to the flow of electron. It's just a concept. It is not true. When we talk about current, this is a huge lie. The current flow from positive terminal to the negative terminal, but in reality, the current is flowing from negative terminal to the positive terminal, because of that's how the electrons flow. Electrons flow from negative terminal to the positive terminal. But anyway, it's just a convention. It doesn't matter. The effect is same, so people never bother to change that. Everybody think the current flows from positive to negative, but in reality, the current flows from negative to positive. But here, this is an n-type semiconductor. It's called n-type because it has so many free electrons. When we connect it to battery, electron starts to flow from the negative terminal to the crystal, and from crystal to the positive terminal. So there will be an electric current. But what if we change the polarity? Like we are connecting the positive negative terminal on this side and the positive terminal on that side. It really doesn't matter. It doesn't affect. So this is not a diode. That's what I'm saying. It's just a semiconductor diode doped with an element like phosphorus and giving so many free electrons, so it is conductive. Okay, so is there any other way to make this semiconductor like silicon crystal conductive? Actually, yes. So this is our silicon nucleus. It has 4 electrons in the outer shell, and we are adding an impurity like boron. Boron actually only have 3 electrons. It doesn't have a 4th electrons. So that space leave vacant. There's a vacancy of electron. So the 3 electrons of the boron share with another 3 silicon atoms around it, and the 4th silicon atom doesn't have an electron from boron to share, so there will be a vacancy for the 4th at the 4th place. So this vacancy is called a hole. We just call it a hole. It's just a vacancy. There is some vacant space. In case if there are some electrons wandering around, this hole can be occupied by that electron. So what just happened? Like we had like a semiconductor crystal, silicon semiconductor crystal. We added boron to it, and this boron created a vacant space for electrons. So the crystal ended up with so many holes, like the vacancy for, okay, let's do with red. So these are holes, means vacancies of electron. So there are no free electrons, but there are so many vacancies of electron in this crystal, semiconductor crystal. This kind of crystal is called p-type semiconductor. That's a p-type semiconductor. So what happens if we connect a battery? That is negative, positive terminal at the wire. What happens? So when we connect a battery, electrons start to flow from the negative terminal all the way here. The electron come at this end and see all these holes. This electron will occupy these holes like that. Then what happens? More electrons are coming, so this electron has to move to the other hole. So it will jump to the other next hole, and from there it will jump to the next hole, to the next hole, to the next hole, to the next hole. So it happens to all the electrons from here, and finally end up all the electron coming from the battery end up on the other side at the positive terminal, and this electron will flow to the positive terminal. So this will continue, like electrons coming from the negative terminal of the battery jump from hole to hole and finally reach the other end and come to the positive terminal. So there will be an electric current. So even the semiconductor doesn't have a free electrons, but it has a vacancy like holes, it can conduct electricity. And if we change the polarity of battery, it doesn't matter. The current will be on the other direction. That's the only thing change. Okay, now the interesting thing. Now let's see how a p-n junction form. So we have n-type. This is the birth of a diode, by the way. So we have an n-type semiconductor here, which has so many free electrons in its lattice, in this crystal. So that's an n-type semiconductor with a lot of free electron. It is conductive, and we are putting a p-type semiconductor on the other side, fusing together. This like p-type. Let's use the red dots. That has so many holes. That's what it has, p-type semiconductor. Like that, putting it together side by side. This is p-type. P-type semiconductor. What happens? You can see so many holes are available in this area, in this region, and there are so many free electrons. What will happen? This free electron can jump to these holes nearby. So some electron, let's say this electron in the front jump to this side, occupy all the holes, all this negative, these are electrons, occupied all the holes. So what happened? Like it occupied all the holes. So all the atoms received an extra electron. When an atom receives an electron, it becomes negatively charged. So we will get a negative charge over here. And from this region, the free electron atoms lost their electrons. They become positively charged. So we have a region here. There is no free holes. So this region is negative. And there a region where atoms lost their free electron and become positively charged. Maybe some more electrons can jump, becoming like that, and here it becomes positively charged, all the atom jumps from this region. So you can see close to this junction, this region lost all the free electron and became positively charged. On the other side, in the p-type semiconductor close to the junction, these holes received free electron, and all the atoms in this region become negatively charged ions. So there is a positive charge and a negative charge existing side by side. Nothing happened to the free electrons here or the holes here. This phenomenon is just happening at the junction, because we know this is like a negative charge. When electron came to these little holes, the atoms here get a negative charge, and this negative charge repel all this free electron coming from the other side, because we know free electrons, the electrons has negative charge, so this will repel. So no more flow of free electron to the p-type region, because here this negative charge exists. So now we have a region here close to the junction. In n-type there is a junction, there's a region with positive charges, and p-type there is a region with negative charges side by side. So it creates a voltage. Usually it is 0.7 volt in a silicon semiconductor. So that is a p-n junction. This junction is called p-n. This junction is called p-n junction. And at p-n junction, in the p-type semiconductor, there is a region of negatively charged ions, and in the n-type region, there is a small region of positively charged ions, and there is a potential, a voltage existing of 0.7 volt in silicon. If it's a silicon crystal, it's 0.7 volt. If it is a germanium, usually it is 0.3 or 0.4 volt. Okay, so that is the p-n junction. We have free electrons and we have some free holes here, and there's a region where no free electrons or free holes, and this region is called depletion region or a depletion layer, and this voltage is called barrier voltage. So what happens if we connect a battery to this setup? So this is a p-n junction diode, by the way. I'm connecting the n-type to the negative terminal of the battery, and positive terminal of the battery is connecting to p-type semiconductor. So what will happen? There is a voltage of 0.7 volt resisting this voltage, so nothing will happen if the voltage I'm applying is less than 0.7, because this voltage can resist this barrier of 0.7 volt. So nothing will happen, no current flow, if it is less than 0.7 volt. But what if I'm applying a voltage V which is greater than 0.7 volt? What happens? This is the negative terminal of the battery. The electrons start to flow from the negative terminal in this direction through this wire to the n region. So we know there are so many free electrons, and also electrons are coming from here. So these electrons coming from here will push these free electrons towards the depletion region to the junction. So this electron will pass this depletion region. Even if there is 0.7 volt, our volt is much higher than 0.7, so it will push the electron through the depletion region to the junction. So the width of the depletion region will decrease and come to the p-type, where there are negative volt. Still we have a lot of voltage. It will still push the electrons further, and the electrons coming will occupy these holes. Then this electron will jump from this hole to the next hole, and from that hole to the next, and finally end up here. This process will continue, like the electron coming from here push the free electrons in the n-type region towards the depletion layer. Then through the depletion layer, this electron will get to the holes in the p-type p region, the p-type region, then ended up on the other side. Then it will come to the positive. So there will be a current flow through the diode, but you only have to apply more than 0.7 volt, because this 0.7 volt acting opposite to the voltage that we are applying. So there will be a current flow. So this is called a forward biasing. The negative terminal is connected to the n type of the diode, n region of the diode, and the positive terminal of the battery is applied to the p region, p-type semiconductor of the diode, and there will be a current flow through the diode. So this is called a forward biasing of diode. So we talked about like this is like a 0.7 volt, but if it's a germanium diode, it's like 0.3. So you don't have to apply more than 0.7 volt. If it's a germanium diode, you only have to apply more than 0.3 volt to conduct the electricity, and this can conduct a lot of electricity, few amperes. So that's the forward biasing. That's how the forward biasing of the diode happening. Now let's see what's the reverse biasing. So we have our semiconductor here. This is n-type semiconductor having so many electrons, and we have the p-type semiconductor on the other side having so many holes. And what we're gonna do, okay, it still have the depletion region, by the way. So this electron will go to the other side at the junction. This is n-type and this is p-type. This is the free electrons from the n side jump to occupy the holes on the p side. So there will be like negative charges on the p side, this where the negative charge, and all the atoms lost their electrons at the n side gain a positive charge, and this is the depletion region, and that voltage is 0.7 volt normally. So what happens if we connect the n to the positive terminal of the battery, and p, this is the positive terminal, p is connected to the negative terminal of the battery? What happens? So here is the positive terminal, positive pin of the battery. So here the free electrons, all these free electrons will flow through this wire into the positive, and left with no free electrons in this region. So when this region lose free electrons, all the atoms there become positively charged. What happens at the other side, where the p area, the p region is connected, p conductor is connected to the negative terminal of the battery? Electrons start to flow from the negative in this direction, then the electron will occupy this space, all the holes. So there is no free holes. So we end up with a semiconductor that doesn't have any free electrons or free holes to conduct electricity. This diode will not conduct electricity because there is no free charge carriers. And you can see this, the depletion region become bigger, like a big depletion region, and the voltage will be higher than 0.7 volt. If it is a silicon semiconductor like a IN4007 diode, it will be like 1000 volt. That would be the voltage barrier across the diode when we connect in reverse bias. So in order to flow the current, we have to overcome this 1000 volts. So how we can do that? Just apply a voltage greater than 1000 volt by the battery. So if we apply a voltage greater than 1000 volt, what happens? Electron come this way to this end, then electrons start to pass through these occupied holes. then it jumps to the positive side, and still it passes through all the positive atom and come to the other side. But it's not easy. It needs a lot of energy. It needs a lot of voltage for this process. And there's a current flow if you apply more than the barrier voltage. And this is a high voltage, and electrons are flowing very fast. It will create some heat, and it will damage the diode. It will heat up the diode and it will damage. And this voltage is called reverse breakdown voltage. That's when the diode break down when we apply a reverse voltage. So we said like this, like 1,000 volt. We have to, if we want to destroy the diode, we have to apply more than 1,000 volt. But usually most of the diode operate at a voltage less than 1,000 volts, so it's just fine. So in the reverse mode, most of the diode will be stand if we are applying less than 1,000 volt. So that is reverse biasing. And in reverse biasing, it generally the diode won't conduct electricity, but there's a voltage called reverse breakdown voltage, which is so high, if we apply more than that voltage, it will conduct electricity and destroy the diode. But there are a few diodes like very small reverse breakdown voltage, like 5 volt or 12 volt. It is designed that way with a very low breakdown voltage, reverse breakdown voltage, which are called Zener diodes. Zener diodes that has some applications. Usually its reverse voltage is like 5 to 12 volt or 30. It depends on how it's designed. So we will talk about Zener diodes in another video, but this is how forward biasing and reverse biasing and how a PN junction diode works. We talk about the depletion region and the barrier voltage and everything. I hope you learned something from this video and it wasn't too difficult to understand or anything. So the whole point of using a diode is to flow the current in one direction and prevent the flow of current in the opposite direction. And there are so many applications for diode. Even the LED, I have an LED here. This is a diode. When we talk about a silicon diode like that, we talk about whenever the current flow through the diode, that some energy dissipate as heat. But in case of an LED, which is also diode, in this diode, the energy is dissipated as light. That's the difference. Okay, so that is a PN junction diode, and we have to remember this 0.7 volt is the barrier voltage. In order to work, in order for this diode to work, we need to apply a voltage more than 0.7 volt. But if it's a germanium diode, it's 0.3 volt. And there are some other kind of diodes actually, which is like even further less than 0.3 volts, like 0.15 volt to 0.3 volt. That's much lower voltage for this diode to work. And those kind of diode are called Shottkey diodes. Shottkey diodes. These are germanium 0.3 volt germanium diodes and 0.7 for silicon diode, which is most commonly used. Silicon diodes. So that's how a diode work. Hope you learned something, and if you enjoy the video, give me a thumbs up, and if you have any questions, just comment in the comment box. I would like to make more videos, and if you wanna subscribe, you will see more videos from me. And that's all for today. Hope you enjoy. Thank you. Thanks for watching. And in the next video, we will just do some more experiment with diode and see this 0.7 volt, where's this 0.7 volt, and 0.3 volt, where it is. Stuff like that. Okay, thanks for watching. Bye.